Welcome to the first lecture of EE557 of this week. In this lecture, we are going to start with a new topic called finite state Markov chains. Let us say finite state Markov chains. So these systems, they are going to be actually quite simple because the state space is going to be composed of a finite set of elements. So what we mean is that our state, xk, is going to be an element of a set with finite number of elements. So the state is going to be able to take only these values, and we see that this is a finite set. That is why we are going to call these systems as finite state Markov chains. In this case, we have therefore xk is a discrete random variable. There is a finite number of elements that finite number of values that xk can take. So we are going to show these states with these circles, and this is the first state, second state, and I have the ith state here. This is time 0, and I can actually here denote time like this. So I have k equals to 0, k equals to 1, and I can show k equals to 3, and I have here these discrete number of finite number of states here, and this is going to continue until a finite time, or it can continue until infinity. So I would have here 1, and I would have I. Okay, so in between we have all of these states, and xk is going to be a stochastic process, meaning that the trajectory that this xk is going to follow among these alternatives will be a stochastic one. Okay? The first stochastic element comes from the initial state distribution. Okay? So at time k equals to 0, we have initial state distribution. And this distribution is nothing but a probability mass function in terms of the probability theory. And depending on the initial state distribution, an initial state will be realized. Okay? Suppose that our initial state was selected randomly as 2, then the state is going to jump to different states, or it might remain at the same state, etc. Okay? So it is going to continue in a discrete manner, jumping between these states, and it's going to end up at a state, let us say, here. Okay? So that is, and here, the initial state is determined stochastically, and also these jumps. So if the state is in one of these finite set of values, then where it's going to jump next is going to be determined stochastically as well. Okay? So here I can actually say that in here transitions are going to be random. And in order to be able to specify that randomness, we are going to define a transition probability matrix. So the only thing that has to be satisfied for these state values, so I have random x0, x1, going until, let us say, xn here. So here I have k equals to n. The only structure that we would like to impose into the probabilities of these states is that we need the Markov property to be satisfied. Okay, by these state values. What that means is that, let me write, Markov property holds, and that means that we have the following equality. Probability, let this be capital P, probability xk plus 1 is equal to j, given xk is equal to I, and given all of the previous states, x0 to k minus 1. Okay? This probability has to be equal to, I will be able to remove these conditionings coming from the past. Okay? P of xk plus 1 is equal to j, and xk is equal to I. Okay? So then how do we specify a Markov chain? The first thing is going to be to specify the initial state distribution. Okay? And the second thing to specify is going to specify how the transitions between these states would be in time. And that specification is made by defining these probabilities. Okay? We will call these probabilities as Pij, and it is the probability that the state transitions to the state j while in the next step, while it is currently at the ith state. Okay? So, for example, the transition from 2 to 1 is going to be P to 1. All right? So let us now learn how to specify a Markov chain. Markov chain. So what about the name here? The name, it is usually, you know where Markovness comes from. It's coming from the Markov property. And usually we call discrete processes like this satisfying the Markov property as Markov chains. So now let us learn how to specify a Markov chain. The first thing to specify is the initial probabilities or initial probability distribution of the Markov chain. And this is specified by giving these probabilities. Probability that x0 is equal to 1, probability that x0 equals to 2, until probability that x0 is equal to I. So we here define a horizontal vector, a row vector, composed of some probabilities, P0, 2, going until P0, I have the number of states equal to I. Okay? So this is a 1 by I vector, and each of these elements here, they are going to be the probabilities. Okay? P0I is nothing but the probability that the initial state is at the ith state. Okay? So then this horizontal vector is just representing the so-called probability mass function of the discrete state xk here. So here, P0 represents probability mass function. Most of the time we abbreviate this with the letters PMF, okay, of x0. All right? And sometimes we call P0 as the initial state distribution. Then what this means is that the state is going to be, at the initial time, the state is going to be equal to 1 with this probability, it's going to be 2 with this probability, and it's going to be I with this probability. So the initial state is going to be random, and its randomness is going to be determined by this row vector. For example, suppose that I is equal to 2, then if I give you P0 is equal to 1, 0, in that case, what does that mean? That means that the initial state is exactly equal to 1, and it is 2 with 0 probability. So I know that in this case, the initial state is going to be deterministically equal to the first state. So my chain is going to start from this state, and it's going to transition to it might transition to the same state, or it might transition to the other states. Okay? Similarly, if P0 is equal to 0.8 and 0.2, this means that the initial state is not deterministic. This means that the initial state is going to be 1 with probability 0.8, and it's going to be equal to 2 with probability 0.2. Okay? So this is the first component of how to specify a Markov chain. Now we can look at how to specify the transition probabilities, how these jumps from one state to the other or from one state to the same state would happen in time. And for that we define the so-called transition probabilities. Pijk is the probability that the state at time k plus 1 is equal to j, given that the probability, given the state at time k is equal to I. Okay? We define these probabilities, and each of these probabilities is called a transition probability. And this is from state I to state j. Okay? So you see that here these I and j would take values between 1 and I. They can take values from this set. Okay? And that means that there is a total of I squared probabilities given like this, and I can actually fill those probabilities into a matrix. Okay? So I can call this matrix the transition matrix at time k, transition probability matrix at time k, and this would be filled with these probabilities P11k, P21k, going until Pi1k, okay, and P12k, going until P1ik. All right. So I have here P22k going until P2ik, and here I have Pi2k going until Piik. All right? So this is called a transition probability matrix. All right? So in this case, you see that here, these probabilities are dependent on time. Okay? So here, I have defined these probabilities dependent on time. So at each time instance, transition probabilities can be different. And at each time instant, we see that this TPM, I can actually abbreviate this as TPM. This TPM can be a different matrix at each time step. Okay? But usually we use a transition probability matrix which is constant with respect to time. Okay? So the dynamics, the transition dynamics or the transition probabilities most of the time do not change with respect to time. That is going to be a specific case that we can consider. And in such a case, when that transition probability matrix is not dependent on time, we call the corresponding Markov chain with a specific name. And here note that this TPM is an I by I matrix. Okay? It is a square matrix filled with transition probabilities. So I will consider the properties of this initial state distribution and the transition probability matrix. But before that, I want to think about the case when the transition probabilities are not a function of time. They are not explicitly a function of time. That case has specific importance for us. So let us make this definition. A Markov chain is called homogeneous. Or sometimes people call it time-invariant. Okay? Time-invariant if and only if the TPM, transition probability matrix, PK, is independent of time k. independent of time k. In other words, I would have pk, which is equal to a constant matrix P, and I would have these probabilities independent of time. Okay? P1i, P21, P22, P2i, going until Pi1, Pi2, Pii. Okay? This is my time-invariant or homogeneous transition probability matrix. So what do we mean by time invariance? For example, in one of the, I can consider a Markov chain, x0, where the state is an element of element number 2 here. So element of a set with 2 elements. In that case, I can have the transition probability matrix at P0 can be, for example, this 0.9, 0.1, 0.1, 0.9. Okay? Then P1 can be 0.95, 0.05, and I have 0.05, 0.95. Okay? If this transition probability matrix, it changes at each time step, or if it depends on the time instant k here, then I would say that the Markov chain is not time invariant. It is a time varying Markov chain, or it's a non-homogeneous Markov chain. Okay? On the other hand, if I have the same Markov chain with the constant transition probability matrix at each time step, then I would call that Markov chain an homogeneous Markov chain. Okay? So in the rest of this lecture, I will consider these homogeneous Markov chains. Okay, the time-varying Markov chains would have similar properties. You can check them from the book. So now let us look at the probabilities, these properties of these probabilities and the transition probabilities. Okay? So the first thing that I'm going to say is that these elements, because they are actually probabilities, they always have to be non-negative. Okay? So P0i, which are defined to be probability x0 is equal to I, they should be always non-negative. Okay? And this is true for I from 1 to capital I. So here I also know that because this horizontal vector is representing a probability mass function of a discrete random variable, when I sum these probabilities, I need to obtain 1. Okay? That is the property of a probability mass function. So here I see that I from 1 to capital I, these P0i's, this is going to be I from 1 to capital I, probability x0 is equal to I, this is going to be equal to 1. Okay? Why is that? Because these are the only possibilities. So the state should be in this finite set composed of elements from 1 to I. Okay? Since I'm summing these probabilities here, that means that this should be the probability of the universal event, and that is going to be 1. You know that these sets are disjoint. These events are disjoint events, and they're also covering the universal set. That means that the total probability should be equal to 1. Okay? So we see here that, therefore, the summation of these elements of the initial probability vector should be equal to 1. Okay? In this course, sometimes we are going to show the same thing with the following notation. So I can write this vector, P01, P02, going until P0i, and in order to be able to sum these elements, I put here a vector which is composed of all ones. Okay? This vector, I will show it as the vector 1. All right? 1, and I will put an arrow on top of it to show that this is a vector composed of 1s. This is equal to 1. Okay? So this is my P0 vector, initial state distribution, and P0 times the vector 1 is going to be the scalar 1. Okay? That is the property of this probability vector. So now let us try to look at the transition probabilities. What are the properties of these transition probabilities here? Okay? So I will define this Pij as P, you know the definition now, xk plus 1 is equal to j given xk is equal to I. All right? And what are the properties that these quantities should satisfy? So the first thing is similar to the first property of the initial state probabilities. So this should be larger than or equal to 0, because these are probabilities. And similarly, when I sum these probabilities with respect to j here, so j from 1 to I, Pij, which is equal to j from 1 to I, these probabilities here, xk plus 1j, xk equals to I, okay? This should be equal to 1. Okay? If I sum these probabilities with respect to I, the sum does not have to be equal to 1, but if I sum these probabilities with respect to j, the sum should be 1. Okay? So remember, in probability theory, if you have a distribution, conditional distribution given like this, if you take the integral of this with respect to x, then you get the result 1. Okay? On the other hand, if you take the integral of this conditional distribution with respect to y, it really doesn't have to be equal to 1. It can even go to infinity sometimes. Okay? So that is why when I take some form of integral, which is the summation here in the discrete random variable, when I sum these probabilities with respect to this argument, I would always get 1. So then what does this mean in terms of this transition probability matrix? In terms of this transition probability matrix. So I see that when I sum these elements, j from 1 to I, Pij, the result is going to be equal to 1, and the result is going to be true for any I from 1 to capital I. Okay? So which elements I'm summing here? If I is equal to 1, I am summing P11, P12, and until P1i. So when I sum these elements in the first row, the result is 1. When I sum the elements in the second row, the result is 1, etc. Okay? So the row sums of this probability transition matrix would be just equal to 1. Okay? So how can I specify such a property? So here is what I'm going to do here. So I will just write the following. So when I take the probability transition matrix and when I multiply it with this vector composed of all ones, okay, then what is going to be the result? I want to multiply this matrix with this vector. Okay? So put this vector here, make it horizontal, and pass it through these elements, and sum and multiply and sum these elements. So you see that the result for this multiplication is going to be, again, the vector composed of ones. All right? So this transition probability matrix would always satisfy such a property. Any transition probability matrix would always satisfy this property. Okay? And actually these properties, these elements of the TPM being larger than or equal to 0 and TPM satisfying this property, they would give us, we would actually give a specific name to matrices that would have this type of properties. And we would call this transition probability matrices having these type of properties, we would call them stochastic matrices. So let us write the definition. An I by I matrix P composed of elements Pij is called a stochastic matrix. If and only if its elements Pij, they are real numbers, satisfy two properties. Pij larger than or equal to 0 when Ij changes between 1 and capital I. And the second property is j from 1 to I, Pij is equal to 1 for all i's between 1 and I. Okay? So now let us try, so that is this TPMs are stochastic matrices. That is the name we are going to give such matrices. We see that this TPM, it is satisfying this type of property. P times a non-zero vector is equal to that non-zero vector. This would really tell us something about the eigenvalues and the eigenvectors of this matrix P. Okay? So I can write the same equation as follows. P times the vector 1 is equal to 1 times the vector 1. Okay? Then this is my A matrix, and this is my eigenvector, and this is eigenvalue, and this is my eigenvector. Okay? So we see that any stochastic matrix has an eigenvalue exactly equal to 1, and one of its corresponding eigenvectors would be this vector 1. Okay? We will write this as a remark here. Remark. The condition j from 1 to I, Pij is equal to 1 is equivalent to the equation P times 1 is equal to the vector 1. But this is equivalent to P times 1 is equal to scalar 1 times the vector 1. This means that, in other words, any stochastic matrix has an eigenvalue lambda I equals to 1, okay, with the right eigenvector EI is equal to the vector 1, vector filled with ones. Okay? So now we have introduced the concept of a Markov chain and how to define a Markov chain. Now we're ready actually for a simple example. Let us say example. This example is going to be the weekly use of a machine. So now we're going to consider a machine, and suppose that we are using it each week. So this time k is going to be denoting the week number. Okay? It's the 0th week. Is going to start, let us say, from today, and it's going to last for 1 week. And then week 1 is going to start, and then week 2 is going to start, etc. Okay? So time k denotes kth week. Okay? And suppose that we are using a machine for some purpose. Let us say that for producing something, we are using a machine, and the state that we call xk represents the condition of that machine. Okay? Let us say that xk is in the set 1, 2, so we only have 2 states. That's going to be a finite state Markov chain. And state xk is equal to 1 represent the fact that machine is operational. Operational. It's not out of order. Machine is operational at week k. Okay? And the second state, xk is equal to 2, is going to represent that. Sorry, this is going to be machine is operational. Is operational at time k, and let us say that state 2 represents machine is out of order. Machine failed at week k here. Okay? These are what these states are actually representing. Okay? Then I will consider the following initial state distribution. P0 is equal to 1, 0. Okay? This represents that this initial state distribution represents that the probability that the machine is operational at the 0th week is 1, and probability that it is out of order at the 0th week is 0. Okay? This means that the machine is initially operational. Machine is initially operational. Okay? So now let us define the transition probability matrix. I will define the transition probability matrix as follows. So I will have here 1 minus q, and I will have q here, and I would have 0, 1. Okay? So now let us try to think about the meaning of this TPM here. So here I have used a scalar that is called q. This q, it denotes the following probability. K plus 1 is equal to 2 given xk is equal to 1. Okay? This is the probability that the machine will become out of order. The machine will fail next week at week k plus 1 when it is operational at week currently, in the current week, okay? At week k. So this is the probability that the machine is going to fail next week when currently in this week it is operational. Okay? There is such a non-zero probability, and that means that if the machine is at the first state, if the machine is operational at the first week, let us say at the kth week, then it's going to, that means that the state is at state 1 here, and then it's going to go to state 2 with probability q, and it's going to remain at state 1 with the probability 1 minus q. So you see that when you sum the rows of this matrix, you would get 1. So this is a valid TPM actually, and it is a stochastic matrix. And here, when you look at a transition probability matrix, you can actually consider the following. This is when the state is at 1 at time k, and this is state at 2 at time k. This is state 1 at time k plus 1, and this is state 2 at time k plus 1. Okay? So this probability here is the probability that state is going to go from 1 to 1. Okay? This is the probability that the state is going to be equal to 1 in the next time step when it is equal to 1 in the current time step. Okay? And the other probability is nothing but the state is going to be 2 when currently it is equal to 1. Okay? This is the probability q. And when you look at the second row, this is the transition probability from state 2 to 1. Okay? So when the state is when the machine is not operational, the probability that it's going to be operational next week is 0. Okay? And when the machine is not operational, the probability that it's going to remain operational in the next week is just equal to 1. Okay? So you see that it is really difficult to actually be able to work with a transition probability matrix like this. So sometimes, actually most of the times, we show these Markov chains with a diagram like this. This is state 1 and this is state 2. All right? So we put some arrows like this. This arrow has probability 1 minus q. This arrow would show that the state is going to remain at 1 with probability 1 minus q. And the state is going to go to 2 with probability q. Okay? These two arrows represent the first row of the TPM here. The first row of the TPM represents the probabilities when the current state is at 1. Okay? And the second row is represented by the arrows going out from this second state. Okay? So we see that the probability that the state 2, from state 2, the state is going to be 1 is equal to 0. Okay? So I do not even put an arrow here from this state to this state. But here, the second state is going to have an arrow to itself with probability 1. Okay? So this diagram actually shows that state transition probability matrix, okay? And it summarizes that transition probability matrix, and we can see all elements from here as well. So here let us try to understand. If the machine is currently operational, if we are at this state, in the next time step, we are either going to remain in the same state, machine is not going to go out of order, it's going to remain operational with probability 1 minus q, and it's going to fail. That means the state going to 2 with probability q. Okay? And here, if we are at the state 2 here, then that means that currently the machine is out of order. And what happens is that without any intervention, the state would remain at the state 2. Okay? Because without any intervention, an out of order machine will remain out of order. Okay? It's not going to magically go back to the operational state. All right? So So now let me try to explain the connection of these Markov chains with the theory that we have learned earlier. So here you see that we have only the stochastic process x0, x1, etc. And we know that these are random variables. Okay? These are not deterministic variables now. All right? So that means that type of process, we can just represent this type of process that we have seen like this. F of xk and wk. Okay? So far, the Markov chain theory that we have seen can be represented with such a state description. All right? Here, of course, we don't have continuous variables. These xk values would take only finite number of values, and therefore this process noise here is not really a Gaussian random variable anymore, but we can still represent this Markov chain with a state space model like this with a function f and with some noise, process noise terms. Okay? And here we are not using this type of representation for the Markov chain. Instead, we are using the one-step transition probabilities. Okay? So we are actually specifying these transition probabilities, and we also specify P of x0. P of x0 is given by the vector P0, and this is given by the transition matrix capital P. Okay? And instead of specifying such an equation with some complicated noise definition and with some non-continuous f functions, we are actually defining for the Markov chain the equivalent representation, which is composed of the initial distribution of the state along with the transition distribution. Okay? So now we are going to see, or we are going to ask the following question. So if this Markov chain would be represented with such an equation, then what type of Markov chain would be represented with an equation that contains an input here? Okay? So what type of Markov chain can be represented with an equation that contains an input? Here you see that I don't have any input variable in the earlier Markov chain definition. Okay? But what happens when I include the input into this stochastic dynamics? Okay? In that case, the Markov chain that we are going to obtain is going to be called the controlled Markov chain. Okay? Let us try to examine that as well. So let us say controlled Markov chains. In this case, the state will not change. State is again going to be an element of a set with finite number of elements. Okay? But we are going to have an additional variable, UK, that can be either discrete, so it's going to be again in a finite set, or it can be continuous. UK can be in R. Okay? This is the single input case. If we have multiple inputs, then this can be RM or something else as well. All right? So then how do we specify a controlled Markov chain with the additional input here? The initial state distribution will remain the same. Okay? So I have P01, P02 going until P0I. And this is a 1 by I vector again. And each of these P0i's would be representing the probability that the initial state is at the ith state. Okay? Then what is going to change is that with the input, the transition probabilities are going to change. Okay? So you see that here, For this simple system, the transition probability would be just this distribution, pxk plus 1 given xk. Okay? But for this one, in order to be able to write the transition probability, I need to write xk here and the uk as well. Okay? That means that for such a system, the transition probabilities from xk to xk plus 1. In this case, if this x is a continuous random variable, then this is going to be density dependent on uk. But here, since we are considering a discrete random variables, this is going to be represented by a matrix that depends on the input u. Okay? So that is going to be the difference of a controlled Markov chain from a regular Markov chain. Okay? So here, our probabilities Pij, they're all going to be a function of the input at time k. Okay? And I would have here P xk plus 1 is equal to j, given xk is equal to I. In addition to this variable here, I would also add the current input to the given conditions. All right? But that means that if each transition probability is a function of uk, then the TPM, the transition probability matrix, is going to be a function of uk. Okay? So I would have P11 of uk, P12 of uk. This is going to continue until P1i of uk. So I would have Pi1 of uk going until Pii of uk. Okay? So I would have an I by I matrix, each element of which can depend on the input. Okay? So this is similar to such a system. Okay? The input modifies the transition of the state from xk to xk plus 1. Okay? Here, similarly, the transition probabilities from xk to xk plus 1, they are modified by the input. Okay? So now I'm going to actually reconsider this machine example, and I'm going to add an input to that Markov chain. We had a Markov chain with the machine example. We had a Markov chain without an input. Now I'm going to consider the same Markov chain but with an input. Okay? So let us say example again. This is weekly use of a machine with maintenance. Okay? In this case, again, xk is going to be an element of the set composed of elements 1 and 2. And state 1 is going to be, again, representing the fact that the machine is operational at time k, and state xk equals to 2 representing the fact that the machine is out of order at week k. Okay? So I'm going to define an input here, uk, and I will not define a continuous input, but instead I will define an input which is in a finite set. So our input is going to be always in the set, let us say 0, 1, 2. Okay? These are the set of inputs that we can have in this case. And these inputs are representing the following. The input 0 represents, let me say here, uk equals to 0 represents no maintenance at week k. Okay? uk equals to 1 represents light maintenance at week k. And uk equals to 2 represents heavy maintenance at week k. All right? So then what did we say? The initial distribution really does not depend on the input at all. So I can actually say that the initial distribution for xk, x0, would be just the same distribution. The machine is operational at week 0. Okay? And then I can look at the transition probabilities. So what was the transition probability matrix that we used earlier? So I have here 1 minus q, q, 0, 1. Okay? So this type of transition probability matrix, we are going to select the elements of a transition probability matrix based on the input value here. Okay? So here you see that when the machine is at state 2, it was going to remain at state 2 in the next time step, according to this transition probability matrix. Here, we have also a maintenance input. Then that means that as the amount of maintenance increases, the machine can actually go back to state 1 as well from the out of order state. Okay? So now let us try to write the transition probability matrices. So let us consider P0. P0 means that the input is 0, so we don't have any maintenance. In that case, what are the transition probabilities going to be looking like? In this case, let us say that the machine is going to remain at the operational state with probability 0.8, and let us say that the machine is going to go out of order with probability 0.2. Okay? And suppose that the machine is not operational currently, then it's going to, without any maintenance, the machine is going to be non-operational. It's going to remain non-operational, and there will be 0 probability going back to the operational state. Okay? This is a transition probability matrix for the no maintenance case. Let me try to write the transition probability matrix for the light maintenance case. Okay? In this case, we have additional maintenance on the system. Okay? But the additional maintenance is just like a light one. Okay? So I know that this is going to, when I have light maintenance, if the machine is operational, the probability that the machine is going to remain operational is going to increase a little bit. Okay? Suppose that it's going to be 0.9 and it's going to go out of order with probability 0.1. All right? So we see that the light maintenance compared to no maintenance increase the probability that the machine is going to remain operational when it is operational. Okay? And what about the other state? If the machine is not operational, now I know that with the light maintenance there will be a way for this Markov chain to transition from the second state to the first state. Okay? So here I will just write the following probabilities: 0.6, 0.4. So with the light maintenance, when the machine is not operational currently, it is going to remain non-operational with probability 0.6 because we only have light maintenance here, and it's going to go back to the operational state in the next time step with probability 0.4. Okay? This is a transition probability matrix with the input 1, and I will finally consider the input 2. Heavy maintenance. In this case, I will assume that if the machine is operational under heavy maintenance, it's always going to remain operational. Okay? So these are going to be 1, 0. Machine is never going to go out of order. All right? And I will assume that if the machine is not operational currently, it is going to go back to operational state with a high probability, and it's going to remain non-operational with a low probability 0.1. Okay? Then this additional input would give us some opportunity to affect the transition of the states. Just like this case. By changing this input here, I can actually try to actually avoid the effects of this process noise. Or I can actually change how the state transitions from xk to xk plus 1. The way to do it in a Markov chain would be to make the transition probability matrix a function of the input that we can select. All right? So in this case, our new diagram would be looking like this. So I would have P12 of which is a function of u, and P11, which is a function of u, P22, which is a function of u, and I would have P21, which is a function of u. Okay? By playing with this input at different time steps, we can change the behavior of the Markov chain, the transitioning behavior of the Markov chain. Okay? So as soon as we define an input for our Markov chains, we can actually talk about controlling the Markov chain somehow. And that brings us to the terminology controlled Markov chains. By changing this input, we can actually try to control the Markov chain. We might try to make the Markov chain have a state that we would like. Okay? So for that, we are going to be talking about not only controlling the Markov chain, but controlling the Markov chain in an optimal way. Okay? And when we talk about optimality in control, that means that we need to have a form of optimization in the procedure. Okay? And when we have an optimization, we need to have a cost function, or we need to have an objective function to be able to optimize. Okay? So here, suppose that we know the cost of the machine being in state xk, while we choose the input uk. What does this mean? So when the machine is operational, we might be earning some money from the quantities that we produce. Okay? When the machine is not operational, when the Markov chain is at the state 2, then that means that we're going to be losing the money that we would be earning from the products that we would produce with the machine when it was operational. Okay? So somehow we need to quantify the states of the Markov chain in order to be able to actually apply the optimal control ideas. I need to know the cost of the Markov chain being at state 1 and being at state 2. Similarly, this maintenance might have a cost. Okay? So, for example, no maintenance, that might have no cost at all, but the light maintenance can have a cost, and heavy maintenance might have an even higher cost. Okay? So I have, if the Markov chain is operational, then I might have no cost, but if it's not operational, then definitely I would be losing money. Okay? As a solution to this, I might apply maintenance to the machine, but that would also cost extra money. Okay? So the cost that we would use here, therefore, should give us the cost of machine being at the state xk while we apply the input uk. So in order to be able to apply optimal control ideas, we need to actually specify the costs of machine being at the state xk while we apply the input uk here. So let us write this as cost of the Markov chain being in state xk while choosing input uk. And you see that this cost function can depend on k explicitly. Okay? So this cost function can depend on k explicitly. Of course, the cost function depends on k through the variables xk and uk, because xk and uk might be different at different time instants. But here, the cost function can also depend on time k explicitly. For example, the cost of machine being non-operational might be actually more costly in some seasons of the year. Okay. So I can write for you two cost functions uk. Okay. Let us say xk square plus uk square. So this cost function, it depends on xk, it depends on uk, but it really doesn't depend on time instance explicitly. Okay? So this is a time-invariant cost function, and it punishes larger states and larger inputs. Okay? I can actually write another cost function, c, let me say xk uk, and this is xk square plus uk square times k. Okay? In this case, this cost function depends on xk and uk, but it also depends on k explicitly. Okay? So this is a time-varying cost function. And we are punishing larger inputs with larger amounts of punishment as k increases. Okay? So if you would like to apply maintenance, we would like to apply it early, according to this cost function. Otherwise, we would pay lots of money for the maintenance. If k is 100, the cost of applying maintenance is going to be quite large, for example. Okay? So now let me try to look at the same example with a cost function. So let us say that we have a time-invariant or stationary cost function. Okay? In this case, therefore, I will just write cxk uk. Okay? And in that case, in the machine example, we have xk and uk as discrete variables. That means that I need to write here my cost for each of the possibilities. Let us say the case when xk is equal to 1, uk is equal to 0. In this case, the machine is operational, xk is equal to 1, and I apply no maintenance. Okay? That actually means that I probably will not have any cost at all. Okay? Suppose that I have the machine operational, and suppose that I apply light maintenance. Let us say that this is 5, and suppose that the machine is operational, and if I apply heavy maintenance, then it's going to be more expensive. Let us say that this has a cost 15. And then I will go to, these are finishing the possibilities with xk is equal to 1. Then I consider xk is equal to 2. uk is equal to 0. I don't apply any maintenance, but the machine is not operational. Then I am not going to be able to produce the products that I'm selling, and I'm going to lose some money there. Okay? So this is going to let us say I'm making these numbers up. Okay? So they don't have any specific meaning, but I'm trying to remain consistent here. So here I have machine is not the cost of machine not being operational with no maintenance. I would have the cost 20, and if the machine is not operational while I apply light maintenance, the cost I will say that it's going to be 25, and finally I would say that the cost of machine being non-operational while I apply heavy maintenance, the cost is 35. Okay? So this is just an example of a cost function. And when I define such a cost function, then I can ask the question, what type of inputs should I select for the system to remain optimal? So I have defined a cost function for each state and the input, but I still did not define how I will combine these cost functions for different time instance. So I would like to apply optimal control in a region in time, for example, from the 0th week to the 10th week, okay? Or I want to apply optimal control from the time 0, k equals to 0, up to infinity, okay? So I don't want to stop anywhere. I want to apply the control forever, okay? But this type of cost function would only give us the cost of a single time step, okay? xk and uk. Okay? So I would like to combine the costs of all time steps, and I'm going to do that by adding these cost functions over an interval. This j is going to denote our total cost function, and I'm going to add the cost functions from time 0 to time n, and I will add them in time like this. Okay? So this is going to be my overall cost function to minimize, for example, with respect to the input. So you see here something interesting. Even though I can select the inputs deterministically, I know that these states would always remain random. Okay? I will not know which states will come in the future. Okay? Even though sometimes I can know what the current state is, if I have complete information, I will not know what the future states would be. The future states are going to be determined by this transition probability matrix randomly. Okay? So before actually seeing the states, I really do not know how to calculate such a cost function because I don't know what xk is. Okay? So I cannot even calculate that cost function before I work with the actual system. So then what to do here? How can I? So this is a stochastic cost function. It changes its value in each realization of the state process. So what can I do here? So here is what we are going to do. In order to remove randomness from this cost function, I'm going to minimize the expected value of this cost function. Okay? So instead of working with the actual cost function here, which is inside this expectation, which is random, I will try to minimize the expected value of this cost function. Okay? So here, this number n denotes the horizon. Okay? So this number n is called the horizon of the optimization. Okay? If n is finite, if n is strictly smaller than infinity, then we call the problem a finite horizon problem. Okay? On the other hand, if n goes to infinity, we call the problem, optimal control problem, an infinite horizon problem. In the earlier case, we have a time interval. When n is finite, we would like to apply optimal control in a time interval, a finite time interval. And when n is infinite, we would like to apply the optimal control until infinity, okay? Forever. So then let us try to look at the control types. The first control type is going to be the open loop control. This is not going to be considered a lot in our course, but I would like to mention about this as well. In this case, I want to choose the input values deterministically. Okay? I want to choose the input values from 0 to n, and I want to do it by minimizing that cost function. Expected value, I have k is equal to 0 to n, ck, xk, uk, and I have this. And I would like to minimize this cost function. Now it's a deterministic one, as you see, due to the expected value. I would like to minimize this with respect to the input variables u0n, and I would like to call the optimal value as u0n star. Okay? So now this is the open loop control case. Deterministic input, open loop control. So now let us look at the closed loop control. In the closed loop control, I do not want to choose the inputs deterministically. I would like to make the inputs dependent on these states. Okay? So I can actually make UK equals to, let us say, GK, and I can make the states dependent on all past and the current state values. And here I'm assuming that I have complete information case. Complete information case. And this is the general case, okay? Suppose that I know what the state is currently, and I know the states in the past, then I can make my input a function gk of the past and the current states. Okay? That is a general case which we are not going to apply in this course. In this course, instead, because here you see that the input is dependent on the past states as well, and that would actually disturb the Markovian property of our chain. So we are not going to be using this because of its non-Markovian properties. All right? Instead, we are going to be using the following feedback form, gk of xk. Okay? So we are going to see that the input in this case is going to be a function of only the current state. All right? And this type of input selection is called a Markov policy. Okay? Because if you select the input as a function of only the current state, then we are going to see that the Markov chain with the input is also going to be a Markov. All right? So with this input selection, we have seen in the earlier parts, we might lose Markovian property. But with this input selection in the feedback loop, we don't lose Markov property. Okay? And that is called Markov policy. Choosing the state choosing the input as a function of only the current state. Okay? But here you see that at each time this function can change. So for example, UK can be x squared at some time, and at some time k, and at time k plus 1 it can be uk plus 1 is equal to 2xk squared. Okay? So if this feedback rule, if it is dependent on time, then we call it actually a non-stationary Markov policy. Okay? So here I can actually call this as non-stationary Markov policy because of this explicit k dependence. If I choose this g function independent of time, okay, in that case we would have a stationary Markov policy. Okay? And in this course we would be considering this type of policies and this type of policies. All right? So let me give you an example here of a stationary Markov policy. Let us say UK is equal to, I would choose no maintenance, I would choose UK 0 if the machine is currently operational. Okay? And I would choose high maintenance or heavy maintenance if machine is out of order. This is like our g of xk. Okay? It's a function of xk, and you see that dependent on what xk is, I choose one of the possible inputs. Okay? So this might be the Turkish style of solving some problems. When the machine is operational, we don't do anything. We don't spend any extra money. So we apply no maintenance at all. And when the machine is out of order, when something goes out of order, we push it to the end. We apply everything that we have to solve the problem. Okay? Or I can actually have the following. I can have the following Markov policy. xk is equal to 1, xk is equal to 2. I can apply all the time light maintenance. Okay? This is in this case a deterministic type of input selection, and you see that we lose xk dependence here. Let us try to change this. So this is my g of xk. This is let us say this is my first Markov policy, first stationary Markov policy, and this is my second stationary Markov policy. So when the machine is operational, we are clever. We still apply a light maintenance to reduce the probability that the machine is going to go out of order, and we apply heavy maintenance when the machine actually goes out of order. Okay? So these are two stationary Markov policies. Why are they stationary? Because these numbers are independent of time. Okay? So here I can actually define actually a non-stationary Markov policy like this. Let us say this is my first feedback policy, this is my second feedback policy. Then I can choose my UK like this. In this case, g1 of k, xk, and g2 of xk, if k is even, when k is odd. Okay? So in this case, you see that depending on k value, this function connecting the state to the input is changing in time. In this case, this would be a non-stationary Markov policy. And these two would be stationary Markov policies. Right? So then, what would the optimization problem look like in the closed loop case? Let us try to consider that. Remember, we are actually minimizing this cost function in time, and in the open loop case, we are selecting the inputs deterministically. So we are minimizing these inputs directly in the cost function, and we select our final inputs, optimal inputs like this in the open loop control. In the closed loop control, I know that these inputs are going to be coming from our feedback policies, okay? So what we have to do in the closed loop control is that I'm going to write the same function, k from 0 to n, ck, xk. Instead of writing here uk, I'm going to write our feedback policy, gk, xk here. Because uk is going to be gk of xk in the closed loop case. Okay? And we are going to try to minimize this cost function with respect to what? Now there is no input there. No input remained here. What are we going to minimize this cost function with respect to? We're going to do the minimization with respect to the feedback policy. We are going to try to find the optimal feedback control, meaning that we're going to try to find the optimal feedback function, gk. Okay? So that means that I'm going to do my optimization with respect to all of the feedback rules from time 0 to time n. And when I obtain that the minimum, the argument of that minimization is going to be optimal, is going to give us the optimal feedback policy. Okay? What does it mean to find the optimal feedback policy? We are going to find such functions. Okay? For example, if this is the optimal feedback policy at time k equals to 2, that means that at time k is equal to 2, when I see the actual state during the operation, I will check the state. If the state is going to 1, I will choose my input 1 there. If the state at time 2 is equal to 2, I will choose my input 2 there. Okay? So that is what selecting the feedback policy would mean. We would find the optimal feedback policies, and when we actually see the actual state during the operation, we are going to select our input based on such functions. Okay? So this was the closed loop case here. But you see that in order to be able to calculate these cost functions, in order to be able to apply some optimization, the first requirement is that I need to know what the cost function is. Now we know what the cost function is, and now I would like to know how to calculate that cost function. Okay? So here you see that in the open loop case, I need to take an expectation here, expected value of these quantities. In the closed loop case, I need to again take the expected values like this. Okay? So the question is, how do we take these expected values? I know that expected values can be distributed into summations here. So I can actually write here k equals to 0 to n, expected value ck, I would have xk, gk, xk here. Okay? So I need to calculate an expected value at time k, which is like this. Okay? Sorry. How to calculate such expectations? That is going to be actually our next question, and we will learn how to calculate such expected values. I will try to generalize this problem like this. Suppose that I have a function of the state of a Markov chain, then how to calculate such an expected value. In the next lecture, we will start by learning how to calculate such general expected values, and in the later parts of this course, we're going to apply that theory to this type of more complicated cost functions. Okay? But that is all for this lecture. Bye.